Hi everyone, hope you are doing well. I'm Reza, founder of the optimizationcity.com. In this video, we are talking about the revised simplex methods. Let's get started.
Let's work to the general form of the simplex method, which is called revised simplex method. The revised simplex method is another practical way to solve the linear programming model. While the simplex method is suitable for manual calculation, it may not be efficient enough to solve the large problem using the computer. This is because it stores information that may never be used in a simplex iteration. For example, some variable may never meet the necessary condition to be selected as the input variable, meaning that all calculation related to the coefficient of those variable in the objective function and constraint will unused. In other words, the column corresponding to that variable is calculated but is not actually used. The revised simplex method used the all principle and step of the original simplex method to solve the problem. However, it avoids performing a redundant operation and storing the useless information that would require a lot of memory on the computer. To apply the revised simplex method, you need to use a matrix formation. This makes it necessary to define the metric formation of the LP model. To represent the standard linear programming, we use the matrix as a follow. Let's see the following model as a matrix. So we are going to maximize z is equal to c times x. A subject to a times x is less than b bar and x is non-negative, where x is a vector including the x1 till xn, c is a vector as well, c1 to xn, a is a matrix that includes the coefficient of the variable for the functional constraint, and b bar is a vector that includes the right hand side of the constraint. In this example, we write a model as a matrix representation. So x is a vector including x1, x2, and x3 as a three decision variable. C is the coefficient of the decision variable in the objective function as a vector. A is the coefficient of the variable in the constraint as a matrix 2 row and 3 column, and b bar is the right hand side of the constraint. So we are going to maximize c times x. In the case of adding a slack variable, the problem becomes as follow. So we have s as a slack variable as a vector including s1 to sm. M is a number of variable. So a comma I is a matrix that show here that all zero except from the diagonal. Okay, it's equal to 1. So this is the matrix representation of the model with the less than model, with the less and equal equation. So this is the general form of that model if you want to add the slack variable. Here, let's see more. Let's talk about this model a little bit more. After adding the slack variable s, you can display the model as a follow. The number of basic variable is the same the number of the constraints. So we have the 3, we have the 2 slack variable, and we have the 2 constraint here. Okay, which is m is equal to 2 in this case, and a comma I has the m row excluding the non-negative constraint, and m plus m column including m basic variable and n non-basic variable. In this example, m is equal to m and n is equal to 3. The matrix a comma m is divided into two matrices. One consists of the coefficient of the basic variable and the other consists of the coefficient of the non-basic variable in the constraint. So this is the coefficient of the basic variable and this is the coefficient of the non-basic variable in the constraint. The matrix of the basic variable coefficient is represented as a b. This is b and this is n, and the is a matrix of the non-basic variable coefficients. Similarly, all variables of the problem, xj and si, are divided into two groups: basic variable, which are s1 and s2, and xn, or non-basic variable, which are x1, x2, and x3. Let's solve the following model using the revised simplex method. In the example, we have the two constraint of three decision variable. So the starting table for the solving problem is as follow. Basically, in this table, you have basic variable s1 and s2, which are slack variable. S1 and S2 is a slack variable, and x1, x2, and x3 is a non-basic variable, which are the decision variable. Matrix B represents the coefficient of the basic variable, while the xn is the coefficient of the non-basic variable. So A is a coefficient, n is the coefficient of the all variable in the constraint, b is the coefficient of the basic variable, which are s1 and s2. Here, this is b, and I is the matrix that we defined earlier, and n is the matrix of the non-basic variable. So x1, x2, and x3 is a non-basic variable, and this is the coefficient of the three variable in the constraint. This is the table for the first iteration of the simplex method, and in this table, xb is x3 and s2, and xn, x1, x2, and s1. Basically, B is a matrix containing coefficient of the basic variable in the starting table, and B inverse and its inverse matrix. The coefficient of the x3, this is the basic variable, it's 3 in the first and second constraint. So let's go to the first table. This is x3 and 3 and 3. This is the coefficient of the x3 in the first and second constraint. And s2 is the coefficient of the s2 in the first table. So we can see the 0 and 1 as here. Okay, and n is the column, the coefficient of the non-basic variable. And this is the B inverse, the inverse of the B matrix. This is the final table of the simplex method. The matrix B is the coefficient of the basic variable in the initial table. We have the x3 and x2 as a basic variable, and the coefficient of that variable here, x2 and x3, 1 and 2. Okay, the coefficient of the x3 and x2, and n is the coefficient of the x1, s1, and s2 in the initial table. So, and this is the B inverse, and you can see that we have the optimal solution in this table. So let's go to some more general definition of the revised simplex method. Using the above explanation, we can now express the linear programming model in the matrix form. The constraints for this model are written as follows. The variable in the LP model can be classified in two groups on the decision and the slack variable. So this is the decision variable and this is the slack variable. They can also be categorized in the basic and non-basic variable, which is expressed as follows. If we multiply the both sides of the equation here by B inverse, we will have this equation. Since xn represents the non-basic variable and have a 0 value, we have as a result this. Given the B inverse for each table, the above equation here provide the value of the basic variable on the value of, or the value of the right hand side of the equation for that particular table. By classifying the variable into the basic and non-basic variable, you can express the objective function as follows. This is the objective function. Given that xn denotes a non-basic variable and with the value of 0, you can conclude that the z is an objective function for a special table is equal to C sub B inverse B bar. Using the above relationship, the coefficient of the non-basic variable xn in the objective function is expressed as follows. This is the coefficient of the non-basic variable. Here, this is the coefficient of the non-basic variable, and we define here. The coefficient of the non-basic variable xn in the constraint can be determined as follows. So this is the coefficient of the non-basic variable in the constraint. And the n matrix represents the matrix where each column corresponding to a single non-basic variable. So that is the coefficient of the non-basic variable in the constraint. Each column of the n displays the coefficient of the non-basic variable in the constraint. As a result, you can use the following relationship to determine the pivot table numbers. So this is the column of the non-basic variable for the special table in the simplex method. To better understand the application, we have the following example. We use the this AJ for ratio test. We will discuss in the following example. So let's say we want to obtain the value of the simplex table with x3 and x2 as a basic variable. So x3 and x2 is a basic variable. C sub b is the coefficient of the x3 and x2 in the objective function. So Cn is the coefficient of the x1, s1, and s2 in the objective function. B is the coefficient of the x3 and x2 in the constraint. B inverse is inverse. Xn is x1, s1, and s2, and xb is x3 and x2. So what is the coefficient of the non-basic variable in the objective function? So we have this equation, and we will find that the coefficient of the x1, s1, and s2 is 1, 1, 1. In the simplex method, the value of the xb and the z is calculated as follows. So this is the right hand side of the constraint, and this is the objective function is equal to 17. The calculation of the x1 variable column is done as follows. So x1 is a non-basic variable, and we are going to calculate the column between the column below this variable. So it's here. We cover all necessary information to introduce in the revised simplex algorithm. Let's proceed the detail of the revised simplex, and we will learn how we can use the matrix representation for solving this revised simplex method. So this is the first step. In the first step, we identify the input variable. In each iteration, use here C sub B inverse n minus Cn formula to find the non-basic coefficient in the objective function. If all variables are non-negative, the optimal solution reach, and we have the optimal solution. To obtain the optimal solution, we use here xb is the optimal solution for basic variable, the other is 0, and z is optimal solution for objective function. If any calculated coefficient are negative, choose the variable with the most negative coefficient as the input variable. Step 2 of the revised simplex method involved determining the output variable. To do so, we need the coefficient of the input variable in the constraint and the value of the right-hand side. If xb is the input variable, its coefficient in the constraint can be computed using the following equation. To determine the value of the current basic variable, which is equal to value of the right-hand side, use this equation. The basic output variable is obtained by this ratio test. The basic output variable can be obtained by following minimization, which is called ratio test in the simplex methods. The step 3 of the revised simplex algorithm involving the calculating the newbie inverse for the new basic variable. Once done, we return to step 1 and pursue the algorithm again. Let's consider the following example as an example and use the revised simplex algorithm to obtain the optimal solution. We have the three decision variable and two constraint, the less than or equal. So we add the two slack variable as a follow, and we start the revised simplex. In the first iteration of the revised simplex methods, we perform the following step. Determine the input variable. S1 and S2 is a basic variable in the iteration with the coefficient of 0 in the objective function. C sub b is 0 and 0. We need to calculate the coefficient of the non-basic variable xn, x1, x2, and x3 as a follow. So this is the coefficient of the non-basic variable, -4, -3, and -6. Because the coefficient of the x3 is -6, which is most negative value, x3 is chosen as the input variable, as shown in the table below. So we have the 3 value, and the -6, which belongs to x3, is chosen as the interim variable. In step 2, we determine the output variable. We calculate the coefficient of the x3 in the constraint as follows. Because the smallest value corresponds to the basic variable S1, we select S1 as the output variable. So we do the ratio test, and we will find that S1 is the output variable. And this is the calculation of the rest of the table we need to pursue the revised simplex methods. In step 3, we calculate the newbie and bxp. Because S3 is an input variable and S1 is the output variable, the basic variable for the new iteration is as follows. Let's go to the next iteration. In the second iteration of the algorithm, we perform the following step. Determine the input variable. We calculate the coefficient of the non-basic variable in the objective function. Xn is x1, x2, and s1 as a follow. So you can see that x2 is a input variable because this is the only variable that has the negative coefficient in the objective function. In the step 2, we determine the output variable. We do the ratio test, and you can find that S2 is the output variable because it has a minimum value in the ratio test. In step 3, calculate the newbie and xp. Because x2 is the input variable and s2 is the output variable, the basic variable for the next iteration is as follows. Okay. In iteration 3, we perform the following step. Determine the input variable. We calculate the coefficient of the non-basic variable in objective function, which are xn is x1, s1, and s2. Because all the coefficients are non-negative, they are 0 or positive, we reach the optimal solution. This is the end of the revised simplex methods. Thank you so much for watching me. If you are any question and need any assistance, please do not hesitate to contact us by email or by filling the contact form in our website, which is www.optimizationcity.com. Thank you so much, and goodbye for now.